A long, long time ago, our ancestors gazed up in the night and they saw a bright band of light stretching across the sky. But what could this luminous phenomenon have been? Was it actually milk, as described in the ancient myths of Egypt and Greece? Was it an obstacle to cross, as suggested by the Silver River story from Eastern Asia? Perhaps it was a map, or a pathway of the birds, as Northern Europeans called it. Or maybe it held the universe together. Southern Africans referred to it as the backbone of night. After millennia of studying that strip of light in the night sky, scientists have now mapped out our Milky Way galaxy, even creating a high-resolution, three-dimensional model that shows the locations and movements of nearly 2 billion stars. That means we not only have a detailed picture of what our galaxy looks like right now, but we can fast-forward the movie to see where things are headed, and even rewind it to see how our galaxy formed. Mind-blowing. Today on Nova Now Universe Revealed, galaxy formation and design. You know, the easy stuff. I'm Alok Patel.
Here on Earth, people look for fossils under the ground to try to reflect back on the history of the ground and history of Earth. So I do the same, but with stars.
Rana Ezzedine is an astrophysicist, cosmologist, and a galactic historian at the University of Florida.
I dig for the oldest stars in the galaxy and in other galaxies in order to trace them back to understand the history of our Milky Way. I do call myself the Indiana Jones of the galaxy sometimes, but you don't have to call me that.
Whoa! Indiana Jones of the Galaxies is a very cool nickname. So let's say we want to cook up a Milky Way-style galaxy from scratch. First, we need a list of ingredients. All right, chefs, start with the generous portion of gas. As much gas as you can get. The more gas there is, the stronger the gravity will be. And it's gravity that enables stars to be born.
What happens is that the gas will start collapsing on itself, and when it collapses, it starts rotating.
So when the gas in our proto-galaxy starts collapsing due to gravity, it'll start rotating, effectively stirring itself. It's pretty convenient in our intergalactic kitchen.
And so this rotation usually flattens out the galaxy.
Imagine making a pizza. If you throw that ball of dough straight up into the air, it'll come back down as a ball of dough. But if you spin the pizza dough as you throw it, it stretches out and flattens.
When we look into the night sky, we see this beautiful strip, the Galactic Milky Way disk. So this is actually how it came to form because of the rotation of the whole ingredients of our galaxy.
All right, chefs, to keep the galaxy from flying apart, we need an ingredient that's invisible. Astronomers call it dark matter. It's what holds the structure of our galaxy together.
Dark matter is this secret agent that kind of glues everything together. We just don't see it because it's dark. We only infer its presence because there needs to be much more mass than what we're measuring from stars.
If there were no dark matter, the stars toward the outside of a galaxy would travel at a slower speed than stars towards the center, where the galaxy's gravitational force is focused. Since we observe the outer stars traveling about as fast as inner stars, we infer there's another source of gravity we aren't able to see. So it's dark matter that gives our galaxy its current structure.
It's there, it's interacting gravitationally with the baryons or the elements that make up the universe, but we just don't see it.
Finally, chefs, to the center of the galaxy, add one supermassive black hole. But, and this is important, there's no off-the-shelf supermassive black hole. You've got to build it up from tinier black holes.
And so what happens is that they start to collide together or attract each other toward the center of the galaxy where most of the mass is located. And this is what forms the supermassive black hole, this giant hoover that is just eating everything around it, including light. So even light cannot escape it, and this is why we call it a black hole.
Now that things are in motion, set that oven timer for a few 100 million years. Our galaxy's ready. Let's take a peek.
We now know of two main types of galaxies, or two main shapes of galaxies.
The first are elliptical galaxies, which are blob-like. But ours looks more like the second type we call spiral galaxies, which includes the Milky Way.
Meaning that it's this galaxy which has a really big bulge at the center, and then it has these spiral arms that come out of it, and it's surrounded by something we call the halo.
I'm curious how we were able to figure out the shape of the Milky Way if we're in the middle of it. I can't even wrap my head around this.
That's a really good question, because before we had such advanced technologies to look at the night sky, people have always wondered about where we are and why do we see this white strip in the night sky. They realized that there must be something called a disk, or there must be a disk to the Milky Way, where we are located somewhere inside of this disk. Because if instead we were seeing a spherical distribution of the matter, it would be all around bright.
So if our galaxy were shaped like a sphere, the stars would be scattered evenly across the whole sky, instead of concentrated in a bright line. But since we do observe the Milky Way as a bright band of stars, astronomers deduced we're inside a spiral flat disk galaxy. If you picture our galaxy as a giant pizza, then our view from Earth would be from a topping, like jalapeno, my favorite, looking across the pizza to the outer crust.
And today, of course, with advanced technologies, such as one of the most important telescopes or spacecrafts called Gaia, which for the first time allowed us to draw the most high-resolution map of our Milky Way, which confirmed what we have been doing for a long time, confirming that we are in a spiral galaxy.
Could you tell us more about Gaia? It just seems so cool to me, like how it works and what exactly it's been allowing us to see.
So let me just give you a brief kind of history about how we observe stars. Usually we go to our telescopes and we observe a single star at a time. And then over the past few decades, I would say, particularly in the past decade, people started looking at stars using surveys, meaning having a telescope on the ground, look at the night sky all night long and collecting as many stars as there is. But for these observations, we have nowhere been able to really look at all of the stars all at once.
We can't view all the stars in our galaxy from one single point on Earth. First, the atmosphere gets in the way. Plus, you can only hope to see about half of them. If you're in the northern hemisphere, let's say you stand on the North Pole and you look up, you see different stars than if you stood on the South Pole and looked up, which would be like looking down through your feet from the North Pole if you could see through the Earth, but you obviously can't, and you see why this is confusing. Anyway, to see them all, you need to get off this planet. That's what I'm trying to say.
We needed a spacecraft. We need to send it to space and let it collect much higher resolution data on our stars.
3, 2, 1, top, décollage.
The European Space Agency launched the Gaia mission in December 2013.
And so Gaia's mission was to measure the astrometric properties, which is positions plus velocities, of about 1.5 billion stars in our Milky Way.
Even though Gaia has surpassed its goal and studied more than 1.5 billion stars, that's still roughly 1% of the stars in our galaxy. And yet, Gaia's measurements thus far have already transformed our understanding of the Milky Way.
It's kind of like everything was blurry, and now we can see so clearly because not only do we see these static lights in our night sky, but we can know where they came from, where they're going, and how they're moving. So we can create kind of a moving map of our Milky Way, not just a static one.
Gaia not only confirmed that we are indeed inside a spiral-shaped galaxy, it helped reveal other details about the Milky Way structure, like the fact that it's actually divided into two pieces, a thin disk and a thick disk.
Our solar system is located in the thin disk, and it's one of the youngest parts of the Milky Way, telling us that our solar system is a very young one. As compared to, for example, if we were to observe a system or a solar system similar to ours, but revolving around a different star, let's say in the halo of the Milky Way, then this would be a very old one, because the Milky Way halo is very old.
So when we talk about the Milky Way and we very compassionately say it's our home, and then our local group is our neighborhood. Mm-hmm. Could you use that metaphor and tell us about the other homes, if you will, that are on our block and what other galaxies in our local group look like?
Yeah. One of my favorite local group galaxies are the Magellanic Cloud, which we beautifully see in the night sky if we were ever in the southern part of the hemisphere. So I used to go observing in Chile a lot, and it's so beautiful because they're as bright as the Milky Way disk.
If you're in the southern hemisphere, you can view both the large and small Magellanic Clouds, which are irregularly shaped satellite galaxies, meaning they orbit our Milky Way.
Now, if we go a little bit farther, we know another very famous and important galaxy that is in the local group called Andromeda. So Andromeda is the closest large-scale galaxy in our local group, and we know that the Milky Way and Andromeda are already interacting with each other gravitationally and actually are meant to merge at some day together to form a different type of galaxy called an elliptical galaxy. So spiral galaxies, when they merge, they convert and become an elliptical galaxy.
Scientists predict the Milky Way and Andromeda galaxies will start to interweave in roughly 4 billion years. But this won't be the Milky Way's first merger.
Other mergers that have already happened with the Milky Way, such as one called Gaia Enceladus. So this was a dwarf galaxy, much smaller than Andromeda. This is a galaxy that now, with Gaia, we are seeing the remnants of it inside the Milky Way, meaning that the Milky Way has already ingested this galaxy and has many of its stars already accreted onto our Milky Way. And we can identify these stars because they look different, they move different, and also they have a different chemistry than our local stars that have been formed in the Milky Way.
Now, let's say one of these collisions happens right now. Let's say it happens tomorrow morning. Would this affect life on Earth? Is there any noticeable difference that we would see?
So no, and I'm going to say unfortunately no, because what a show that would be. Because these things happen over a very long time scale. So the collision is not really just a collision that all of a sudden the Milky Way galaxy is like, oh, what is this thing coming toward me? It's going to collide. This happens over millions and billions of years, where the gravity starts attracting the other galaxy slowly and ingesting the star slowly. Like the fate for our Milky Way and our Andromeda, eventually they're going to turn off their star formation but continue in this beautiful gravitational dance until they merge. However, what it will do is that sometimes it induces new star formation. So because the gas in the galaxy is being heated by this interaction and more stars are infalling and more gas is infalling from the other galaxy, it starts a new era of star formation where younger stars all of a sudden are basically coming from this merger, and they have two parents. They have both the Milky Way and whatever galaxy has infall.
So no need to freak out. Our merger with Andromeda is billions of years away, and the stars are so spread out, it's unlikely that any of them will collide. Which means we have time for a second half of this episode. When we return, simulating galaxy formation using supercomputers.
So I think from just a human perspective, trying to understand what is the origin of everything is a very interesting question.
Saunak Bose is an astrophysicist at the Harvard-Smithsonian Center for Astrophysics.
And predominantly, I do this work by using large supercomputers to essentially simulate the formation process of galaxies over cosmic time.
Now, while using computers to simulate galaxy formation isn't a new idea, it's been around since the 70s, it's gathered momentum recently as computers have improved.
And essentially the procedure is as follows. We start with some assumptions of what we think the initial conditions of the universe look like. So how did the universe look, say, 13 billion years ago? It turns out that these initial conditions are amongst some of the best measured data that we have available to us, made by space-based satellites like the Planck satellite, which essentially measures the microwave background radiation, or essentially photons that have been liberated from just after the Big Bang, that have been streaming towards us over billions and billions of years, which we can measure and then use to infer exactly what the structure of the universe was like at the time when these photons were created, you see. So this measurement actually provides us a snapshot of what the baby universe looked like.
Baby is a relative term. That, quote, baby universe revealed by the cosmic microwave background radiation was already 400,000 years old. Not so baby.
So we have this as a starting point. And what we then need to do is to basically teach our computers how to evolve these starting conditions over time using the laws of the universe, and then give an end result.
Remember the ingredients we needed to create a galaxy?
Dark matter is this secret agent that kind of glues everything together.
Formulas for dark matter and dark energy are crucial for developing the right computer models for galaxy formation. So Sanok has to know a lot about them to program them into his simulations.
So I think the word dark is in many ways equally an apt description of our inability to actually see what either of these components are, but also an equally apt description of our lack of understanding of what either of these are as well. So it's an absence of knowledge in some sense. Dark matter is probably more easily explained than dark energy is. So it's basically this idea that the universe that we live in is dominated by gravity on these large cosmic scales.
So even though we can't see dark matter, scientists surmise it's out there by studying the behaviors and physical properties of the stuff we can see.
One specific example being this idea of gravitational lensing. So this is an idea that was put forward by Einstein, where he said that as light goes past an object that creates gravity, the path of light actually gets warped and bent, much like how light bends in the presence of a magnifying glass or a lens. And if we look at images of distant galaxies taken, for example, by the Hubble Space Telescope, we see these characteristic warps and stretching in the images of galaxies created by some distribution of matter that exists between us and these distant galaxies that can't just be explained away by any kind of visible material that exists between us and them. And this other way of viewing the universe through this gravitational lensing effect also becomes a very powerful additional source of evidence for dark matter.
So what happens when these computers evolve these starting conditions and ingredients into a galaxy?
This is kind of one of the really odd things, which is that the stuff that we understand very little about, which is the dark matter that we can't see and the dark energy that we know very little about, the physics of those is actually relatively easy to model because it is ultimately the physics of gravity, which we understand pretty well and can represent very well with equations. But for the ordinary matter that you and I are made of, there is a lot more that actually goes on with these things. So, for example, bits of hydrogen can cool and collapse and then form stars, and these stars can then grow and radiate energy, and the stars will then undergo supernovae, and all these kinds of complex processes take place, which we don't need to worry about in the case of dark matter. And putting all of these into a mathematical form that we can then pass on to a computer for it to then pass and then feed back into our models becomes a very, very complex task. And that's something we've only really made progress in the last 10 or 15 years or so.
And is there a certain ratio, if you will, or ratio that's been seen throughout the universe of dark matter?
So when the universe was, say, 400,000 years old, at that point, the amount of dark matter outweighs the amount of ordinary matter by around a factor of 5 or so. So quite a lot more of dark matter than there is of ordinary matter. However, when we actually go around the universe today and look at galaxies, we don't necessarily find this ratio being constant. So there are certain galaxies like dwarf galaxies, which are the really, really tiny galaxies that orbit around the Milky Way, which are very good laboratories for studying dark matter because actually they are dark matter dominated. However, when you go to other types of galaxies like the Milky Way, that ratio is actually less stark compared to what we find it in dwarf galaxies.
For fun, let's try simulating a galaxy without dark matter. We'll just use regular, everyday matter.
I think what would come out at the end is a very different realization of galaxies than anything we think of today. And the reason for this is that stars and galaxies and so on, the reason they're able to form in the very first place is because there was dark matter.
The modeling reveals that the universe not only has a lot more dark matter than regular matter, but the dark stuff is fundamental for creating galaxies in the first place.
And so what actually happens is these halos of dark matter, which are the regions where the dark matter has collected in the highest densities, and gravity has essentially collapsed them into these big balls, if you will, of dark matter. They essentially act as wells, gravitational wells, that are able to draw into them, kind of like sinkholes almost, the hydrogen gas that eventually then forms the galaxies.
That gas is what gets compressed to give birth to stars.
The fact that this process actually happened in the time that it did was because dark matter was already present as the scaffolding upon which this visible universe was built. So we basically need to assume some theory of the dark matter and assume some kinds of properties that it needs to have, which will therefore dictate what equations we put into the computer. And this is kind of how we play this game, really. So we put in a theory and then we get the final result, which we can then compare with the data and then see how well that theory works and then kind of work iteratively.
Scientists experiment with these simulations by inputting different theories and checking on the resulting galaxies. But what theory explains those spiral arm galaxies that they sometimes end up with, like the Milky Way?
The concept of spiral arms is something that people have been wondering for a while, and there are, I think, many hypotheses as to why some galaxies are able to create spiral arms and others are not. But essentially, the idea comes about with the fact that when these galaxies are forming, there are these disturbances and perturbations that take place in the disk where the gas has collapsed and contracted into a region where stars are forming. And these galaxies are rotating as well. And as something is collapsing and rotating at the same time, you essentially have, different parts of the disk essentially moving at slightly different rates from one another. There are certain points in this disk where there'll be an overabundance of gas, under parts of the disk where there's a slightly underabundance of gas. And as this is rotating, what actually happens is in these regions where there's the overabundance, that's where the new stars are preferentially forming. And because of the rotation, this starts creating points where the motions of stars slightly lag behind other points, you see. And this is what creates spiral arms.
By creating and testing these models and simulations, scientists can better understand what goes on in the lives of galaxies.
Galaxies generally have very tumultuous lives. So our own galaxy, for example, doesn't really, kind of live in isolation. So all galaxies undergo a very large number of merger events, and they're constantly bombarded by tiny galaxies and other dark matter halos throughout their lifetimes.
I love that we just described galaxies as having tumultuous lives. In my mind, I'm picturing this galaxy soap opera right now.
Yeah.
Of how much drama they go through.
Yeah.
Turns out that peaceful strip of stars we see in the night sky is only a brief snapshot in the turbulent and dramatic life of our galaxy. By trying out different galactic recipes and binge-watching reruns of these galactic soap operas, scientists will continue their efforts to predict the future and season finale of our Milky Way. Nova Now Universe Revealed is a production of GBH and PRX. It's produced by Terrence Bernardo, Jenny Cataldo, R.A. Daniel, Caitlin Falds, and Jocelyn Gonzalez. Julia Court and Chris Schmidt are the co-executive producers of Nova. Suki Bennett is senior digital editor. Christina Monin is associate researcher. Robin Kasmer is science editor. Robert Boyd is digital associate producer. Shyla Duff is digital video intern. And Devin Maverick Robbins is managing producer of podcasts at GBH. I'm Alok Patel. We'll be back next week with the cure for loneliness, the search for alien life on faraway planets. If you love stories about our universe, visit pbs.org/NovaNowPodcast and check out Nova Universe Revealed, our cosmic 5-part film series airing Wednesdays on PBS and streaming now on the PBS Video app. This podcast has been made possible by the Gordon and Betty Moore Foundation.
GBH.